Hi everyone, I'm JVacek and I'm in EC 331, 311, and EC 341. So today we're going to be talking about the audio amplifier, which is common in almost every cell phone there is today. So we'll first start by talking about an important property of systems, and that's the Fourier transform. And we'll be using this property throughout this to explore different V-ins. So what we notice about a Fourier transform is that if you have a complex sinusoid, pass it through an LTI system, you get that same complex sinusoid out, but plus a frequency response, and that's h of jn omega naught. Now, you're probably wondering, how do we actually write things as a Fourier series? Any periodic function can be written as a Fourier series. A Fourier transform, it doesn't necessarily have to be periodic. So we'll first explore a sinusoidal wave as our input. So suppose our input is v in a t, which is a cosine omega naught t. Now we want to prove that our v out will be a magnitude of h of j omega naught cosine omega naught t plus the phase of h of j omega naught. Alright, so first what we do is we'll start by rewriting v in a t as a complex sinusoid, and we've done that here. Now, we pass that through the system, and what we'd expect is we get that same complex sinusoid out, plus the frequency response, and that's exactly what happens. Now we can use complex symmetry to achieve that desired output that we're trying to prove. And not complex symmetry, conjugate symmetry. So we know from that the magnitude of h of j omega naught is equal to the magnitude of negative h of j omega naught. Now we know the phase of h of j omega naught is equal to the negative phase of h of negative j omega naught. So we rewrite that, do some simplification, and it turns out v out of t from here also equals v out of t up here. Now suppose v in a t is a periodic square wave. And now you can rewrite this, since it's periodic, we can write it as a Fourier series. So we do rewrite it as a Fourier series, and just like usual, what we'd expect is that we get a square wave out as well, plus some frequency response. And that's exactly what happens. But it's not a perfect square wave at its v out of t. It's called Gibbs phenomenon, and what you'll see is there'll be small oscillations and small overshoot when it changes, and that's what happens. And the periodic square wave coming out is due to the Fourier series. Now, actually, let me talk about, suppose we had v in a t, let's go back a slide, is 10 millivolts. And that's okay, I probably should have said this first, but having that still maintains the system as being an LTI system. But now suppose A is 200 millivolts. Now, there's two changes that will happen. If we had a graph of V out of t, we'll notice we won't actually have a perfect sinusoid anymore. So it's not an LTI system. And what that's saying is that when you actually when you have an x of t, pass it through the system, and your output is y of t, you'll actually start seeing, you'll get your x of t out, plus another x squared of t, plus an x to the third of t potentially, or maybe an x to the fourth of t. And each of those different x squared to the x third, they add different leakage frequencies to the output. So you won't get a perfect sinusoid because you'll start seeing more DC values, you'll start seeing an output at higher frequencies than your actual frequency, and that's what happens when you change A to 200 millivolts. You also have to change your V bias. Our V bias, as shown here, or back here, is right here, and our V bias is 0.65, but if you change it to 0.7 with an A equal to 200 millivolts, you will start seeing it's nonlinear. Alright, so now let's look at the gain and impedance of the system. So there's two stages with this circuit. There's a common source and the source follower. So the purpose of the common source is to achieve a high gain. And so from that equation we know V out over Vn is negative GM1, R out 1 parallel with R1. and we know R out is R at 1 parallel with R1. Now you're wondering, why isn't that enough? The issue with that is that R out is very high. And you don't want R out very high because that means most of your voltage is going to be dropping out of your R out and not over your RL. Now, so you need that source follower to lower that output impedance. The issue with the source follower, though, is there's a trade-off. You lose a little bit of your gain because V out over V in is GM2 R out 2 all over 1 plus GM2 R out 2. So you lose a little bit of your gain overall, but you lower your output impedance dramatically. And what that does is now, since you've lowered your output impedance, most of the drop is going to be across RL, so you're delivering maximum voltage to the speaker. Alright, so now let's move on to the speaker itself. So the speaker itself can actually, there is a magnetic circuit within the speaker, and that magnetic circuit is actually, there's a coil wrapped around in kind of a cylindrical fashion around electromagnet, and there's also a permanent magnet it sits within. And so we're going to take a look at just a kind of a typical magnetic circuit and how it can be replicated as an electric circuit, and the IV characteristics and EH characteristics, see how they're analogous. So if we have this circuit right here, this magnetic circuit, we can model it as an electric circuit. And this R naught goes with this air gap, and this R goes with the magnetic core. And what we'll notice here is that the sum of HL is equal to the sum of MI. That's kind of like Kirchhoff's voltage law, and the sum of BS equal to 0 is kind of like Kirchhoff's current law. And what you'll notice is graph of B and H here for the magnetic circuit is analogous to IV curve. And that's because we can multiply the V kind of turns into HL. The E, your electromotive force, is MI, and your current is also BS. And it's similar to those models of transistors where, for like a BJT, suppose, if you have VCE on the x-axis and IC on the y-axis, set with a VBE, you'll notice as you raise VCE, you'll also see saturation, just like a magnetic circuit, which is nonlinear, but we're linearizing it. All right, that's all I have. Thanks for watching.